In this lecture video, I'm going to talk about momentum and impulse, and then we'll start to learn about collisions and conservation of momentum. So if we look at these two scenarios, we have sort of an intuition about what momentum is. So if we look at scenario A, we have somebody hitting a golf ball. If we look at scenario B, we have somebody rolling a bowling ball. So in which scenario does the ball have more momentum? Well, for scenario A, a lot of people want to say A because the golf ball obviously moves a lot faster than the bowling ball does. However, in part B, people want to say the bowling ball because it's heavier. And so we realize that both the velocity of the object and the speed at which it's going affect the momentum of the object. So in this scenario, we can't really tell without actually having some real values for like the mass of the golf ball versus the bowling ball and their relative velocities. But the point is we have this natural intuition about what momentum is. And momentum is an object's mass times its velocity. We write momentum with a lowercase letter p, and then mass times velocity. So the unit that we get for momentum is kilograms times meters per second. Now, if we would like to change an object's momentum, we can apply a force to that object for some time period in order to slow it down or decelerate it. So if I were to throw an egg at the wall would nearly instantaneously exert the force to change the momentum of the egg from whatever it was to zero, to stop the egg, right? And because all of that force is exerted at one period of time, it makes the egg shatter. Now in class we're going to do a experiment where we test to see what is the difference between throwing an egg at the wall and throwing an egg at a sheet. So if we threw an egg at a sheet has an elastic property, and so we get to recognize or observe this idea of impulse. So impulse is that anything with elasticity, if you throw an object at it, that force is going to be spread over some time period. Or the force is going to be exerted enough to change the momentum of the object in a certain time, not instantaneously. And so there's never one force great enough at any one moment to then break the egg. So we'll test this theory in class. But the equation for this is that force is equal to mass times acceleration. We learned that that is Newton's second law. We know that acceleration is the change in velocity over time. So we define impulse as force times time, this is actually impulse, is equivalent to the change in the momentum of the object. So let's just go back up again and look. So we see m times the change in velocity here. So if we multiply the t on this side, we get ft equals m times the change in v, or ft equals the change in m times v. Okay, so let's go ahead and actually look at some other scenarios of this. I've pulled up a couple of YouTube videos. We're going to watch those, and then I'll show you this graphically. So here is actually a picture. One of my students actually told me about this. So this is a picture of a golf ball hitting a wall. So you'll notice that the golf ball, although we don't think of golf balls being elastic, this is a golf ball hitting a steel wall, or a steel wall in super slow motion. So you can see how the golf ball, because it's elastic, it's going to distribute the force in order to change the momentum. Therefore, it's never great enough to shatter either the wall or the golf ball. Let's look at this. This is the idea of an airbag. So airbags are designed so that the force it takes to change a person's momentum when they're in a car accident is never great enough at any one time to do as much damage as if they were to hit something that was non-elastic, like the steering wheel or the windshield. So here there's two. You can see that as the crash test dummy hits, they are absorbed into the airbag, and therefore it distributes the force to change their momentum and stop them in an extended period of time rather than instantaneously, preventing damage from occurring. Okay, so let's go back and talk about one more thing in this video. So sometimes the force that is applied during impulse is constant. So the same force is being applied during the duration of the force in order to change the momentum. But sometimes the force is either increasing or decreasing. And this typically happens when we have elastic things, because we know, based on the idea of Hooke's law that we discussed last time, that the further you stretch something that's elastic, the stronger the force that is applied at that moment. So when we have this idea of changing forces, we would say that the force average times the time is equal to the change in momentum. And we will always be dealing with a linear relationship for our purposes, saying that force is changing at a constant rate. So let me just give you a graphical example of this. So let's say you were given a graph that looked like this, that had force on one axis and time on the other, and it asked you what was the change in momentum for this scenario. Well, what we would actually do is we'd have to take the average force times time to get the change in momentum. And because this is linear, it's a constant change, so we can take the average of this just by taking 10 plus 40 and dividing by 2. So 10 plus 40 divided by 2 would give me 25 newtons is the average force being exerted over the time period. Then if I look here on the bottom axis, so I start and go from 0 to 20 seconds, so that's just going to be 25 times 20. Let me grab a calculator because I don't well, I guess I can do 250, so that'd be 500, right? 500 newtons times seconds. And that would be the change in the momentum or the impulse for this scenario where we actually had a constantly changing force.